Um, can everyone hear me?
Yes, I can hear you.
Good evening, everyone. Good evening, everyone. It is truly a privilege to stand before you today as we come together for this enlightening session. Talks like these provide us with unique opportunities to engage with thought leaders and pioneers who are shaping the future of science and technology. It is my honor to welcome you to today's podcast. We are privileged to have with us Dr. Varun Raghunathan, an associate professor in the Department of Electrical Communication Engineering at the Indian Institute of Science, IISc, Bangalore. Dr. Raghunathan earned his PhD in electrical engineering from the University of California, Los Angeles in 2008, specializing in nonlinear optics and integrated photonic devices. Before joining IISc, he gained valuable industry experience as a research scientist at Agilent Research Labs, focusing on biomedical imaging for cancer diagnostics and its clinical applications. His extensive experience and expertise make him a leading figure in his field. Today, Dr. Raghunathan will share his insights on advancements in science and technology, drawing from his extensive research and professional experience. We are eager to learn from his experience and knowledge. Please join me in welcoming Dr. Varun Raghunathan.
Thank you very much for the introduction. Let me quickly share my screen. Can you let me know if you're able to see my screen?
Yes, sir, we can see your screen.
Let me try to minimize this. Okay, um, so let's get started. So today I would like to talk about some basics of what we work on in the area of quantum communication. So my lab essentially works on experimental optics, right? We try to build things in the lab, develop some theory models, and then try to do measurements, and then try to understand different kinds of systems. Of particular interest has been can I set up secure communication, right? From between two parties, Alice and Bob, and then ensure that I'll be able to distribute secret keys without any eavesdropper or without the ability of an eavesdropper having or without any eavesdropper without the eavesdropper having the capability to tap into that particular block of communication, right? So how do we go about doing that? I'll describe briefly in this talk. Other than that, we also work a lot on nonlinear optics, which is essentially how, when I focus light tight on a sample, how does that medium behave? So you can think of it like a nonlinear amplifier. I drive it hard enough, the amplifier starts creating harmonics and so on. So we are interested in studying those effects in very different kinds of systems. Like we study them in thin layered materials, we study them in nanostructures, which we fabricate in the clean room. We also get biological samples, like tissue samples, patient tissue samples, and so on, where we would like to study the same nonlinear processes in the tissue samples and use that process as a technique to do imaging, right? I want to map out the tissue, try to figure out whether it's normal or cancerous by using the nonlinear signal, basically. That's the idea. So we worked extensively on experimental optics, and a particular project of interest I'm going to talk about today is in the area of quantum communications, right? So before I proceed with my slides, I would like to know a bit about the target audience here, right? Am I addressing a lot of students or faculty? Maybe Sana, you can tell us what kind of audience we have today. You're muted, I think. Can you unmute and please tell me? Are we having a lot of students or faculty
Yes,
or
sir, all students, all students.
all students? Okay, okay, very good. So I don't know what level of background you have in this area. So this talk is mainly pitched as a tutorial, right? I've given similar talks to faculty as well as part of faculty development programs where people are trying to learn or gain new knowledge about up and coming fields. Right? This talk will also be featured in a very similar perspective where you would learn some of the basics and then what are the recent advances so that if you want to do research in this area or if you find something interesting, you can always go and learn about it. You can search in Google or YouTube, you will find videos or write-ups on some of these topics. You can dwell deeper and understand them, right? That's the idea. Right. So, what is the outline of my talk? I'm going to talk about a little bit about cryptography. Right. Coming from like this is the topic which computer science people talk about, not much in electrical or ECE departments, but still we need to understand a bit about cryptography so that we can build optical systems which will enable secure communication. That's the idea. And then more generically, we'll talk about bit more about quantum communication, which encompasses not only secure key distribution, but even like even a grander goal, like building a quantum internet, for example. What would it take to build interconnected devices, which would eventually form a future quantum internet, right? Then I'll go on to a bit more details about the hardware. What are the basic components which one can use to build a quantum communication link? What are the typical quantum key distribution protocols? I'll briefly touch popular protocols, though these are very old now, right? These are more than 40 years old, the BB84 protocol and the ECART 91 protocol. I'll briefly touch upon how these protocols work and then move on to talking about some of the cutting edge topics in the area of quantum communication and a few concluding remarks, right? So what are the take home messages I want the students to take from this lecture is that I want you to understand what is cryptography first, right? And then what is the need for having quantum communication? And then when we start talking about the basic devices, we'll touch upon what a qubit is, what is a single photon state, what is an entangled state, and so on. These are very basic concepts, right? I'm just going to superficially talk about these things with very little math, basically. If you want to dwell deeper, there are many, many books which are written in these areas, which will take you to essentially lot more depth than what I'm going to talk about, right? But then the whole idea of exposing or giving an idea about these topics is to essentially trigger your interest, so that if you find something interesting that you would want to pursue a career even, then you may want to pick up and learn some of these topics basically. Right? And subsequently, I'll talk about what quantum key distribution is and some ideas about how state-of-the-art QKD systems are built, basically. Right? Few starting remarks. I already addressed this. This talk is focused on basics and applications. I don't dwell in any rigor on the theory or proofs of what I'm going to talk about. This is an actively pursued area of research. You'll find that some of the papers I talk about may be as old as 1984 or even older than that, and some things which may be as new as maybe 2020s even, right? That's the range of research which has happened, and it's still ongoing, right? And there are suitable references which I have provided towards the end, which you can find. And I believe this talk is also recorded, so the references will be available to you as well. Okay, so going on to the basics of cryptography, we are talking about secure communication between two parties, which we call as Alice and Bob, who want to securely communicate, right? So why do you want a secure link? More and more, we are trying to do a lot of e-commerce, banking, everything is net banking. No? If I go to the bank and ask them to, for example, fill a passbook or any of those tasks, they just shoo me away, right? They tell me, oh, everything is available online, you just figure out. Right. So then I come home and log into the internet, log into my bank account. Then I want to make sure that it is secure. Right. I don't want any eavesdropper or a malicious agent getting that information. If any password, for example, the transaction password is revealed, right, then potentially I could be looted of all my money also. Right. So security is very important in the present day world, where a lot of the transactions and the way we do lead our life is going through the internet, basically, right? So in this context, it's very important to understand that the secure information has a shelf life also. What do I mean by that? There are, for example, if there is an OTP to log into my IRCTC account to book a ticket, for example, that OTP lifetime may be 1 hour or even less than that. All the way to if there are some secrets, right? Country secrets or military secrets, about locations or things like that, those need to be protected for even much, much longer time, like hundreds of years, right? So that is what the shelf life of that information is, right? So an OTP needs to be secure only for a very short duration, while there would be even more important secrets which need to be secured for many, many years, basically. That's the concept. And accordingly, the amount of effort you would put to secure that information would also vary, right? An OTP you may not put as much security to that, but military secrets, obviously, you need a lot more higher level of security to protect them, right? That's the idea, right? So then you can talk about what are known as private key cryptography and public key cryptography, basically. What is private key cryptography? Essentially, Alice and Bob have a private key already exchanged, right? Somehow they've already exchanged and it's secure, right? So then they encode that information, whatever information they want to convey with that secure key. For example, here I show a very simple problem. Sorry. Yeah, so I'm not sure if you're able to see my mouse pointer, but what is shown here in the example is that the original message I want to convey is quantum, right? And the mapping is that A is 0, B is 1, C is 2, and so on, right? My encryption key, which is already exchanged, is this garbage, basically, GQYRWAD, and so on, right? So the way I encode my information to the key is by doing a modulo XOR operation and then a modulo 26 operation, because this essentially forms a 26 modulo system, basically. And then once I do that, I end up with my encrypted message. I transmit that to Bob, and then assuming there are no errors, Bob will recover the same message. He runs a corresponding XOR operation on that, and then he'll be able to recover that original message, right? So this concept is known as private key cryptography, and it also this falls under the category of private key cryptography, and this particular XOR type implementation is what is known as the Vernon cipher, basically, which relies on one-time pads, right? So what this kind of communication requires is that the key has to be as long as the message you are trying to encrypt. You need to encode and transmit that, basically. That's the idea, right? And there are rigorous proofs, security proofs, which are available, which show that as long as the key is secure, it is not reused, then I'll be able to guarantee security, basically. If the key happens to be reused, I cannot guarantee security in this kind of implementation, right? That's the idea. Then this became too complicated initially. This was initially followed, but then it became too complex because I need a key as long as the message for me to do reliable encryption, basically. Then came what is known as public key cryptography, where the idea being that Alice essentially sets up something like a mailbox, where essentially that information is put through that chute, basically, right? Where you see this patra, that's where I would put my message, for example. And only the person with the key to open the bottom layer would be able to decrypt the message, basically. That's the idea. So I need two pieces of key, one with which Alice encodes the information and transmits, right, which is equivalent to dropping it in this letterbox. And then Bob has a corresponding key, which is different from that original key which Alice used, but which is sufficient to decode that message, basically, right? So this scheme is very popular. This goes by the name of RSA cryptography, or RSA, Rivet, Shamir, and Adelman scheme. And then you may have come across these kind of keychains which are available, at least in the mid 2000s and all. When my friends were working in companies, everyone used to get one of these keychains, right? So if you want to log into the company's network, one has to use that keychain and the key to essentially secure that particular session of communication, basically, right? So these were very popular. Nowadays, you can also generate it, distribute it through phones, through like similar to OTPs. You can transmit them, basically, right? So this is how this protocol works. I will not go into too much detail in the interest of time, but then what this thing relies on is starting with two big prime numbers, taking the product of them, right? So then if I use a different version of it at Bob's end to do the decryption, then an eavesdropper should have the ability to factorize the product of those two prime numbers, which is computationally a very difficult problem, right? That's the idea. Factorizing that product n into the individual numbers p and q takes a significant amount of time, basically. For example, if I start with two 200-digit numbers, or for example, if n is a 200-digit number, the complexity in this operation could take as much as 10 power 86 or 10 power 80 seconds, basically. Extremely long amount of time will be taken to decode or to decrypt or understand that key. So it is a computationally difficult problem. The security is not based on any rigorous theoretical proof, but it's based on computational complexity, right? So that's where the problem comes in, because if I can come up with better and better algorithms, which will be able to decode that product of those two prime numbers, then I run into difficulty because somebody can easily break that up, right? So with the recent announcements from Google, IBM, and so on, that they have built quantum computers, no, with many, many qubits which are available, 50 qubits. I even lost track of what is the latest number of qubits which have been tested out. But it's definitely 50s and 200s kind of a limit is where people are testing out these quantum computers. Then what happens in parallel? I'll be able to run these algorithms. There are better and better algorithms which have come up, which can be implemented in a quantum computer, that this factorization problem can be done in a much shorter time scale, right? So now, if these quantum computers come at the hands of our adversaries, no, then you can imagine that some of our secrets may not be secure anymore, because as it's transmitted, if they have the capability to tap into that, they can run that through a quantum computer and figure out what that message is, basically. And that's where a lot of problem comes in, that some of the underlying security which has relied on RSA for the last 30 years can be at risk, basically, right? And that's where one has to go beyond these kind of computationally complex problems and has to rely on something which is much more rigorous and guaranteed security based on something much more substantial with rigorous proofs, with something which is guaranteed by some kind of a physical principle, basically. That's the idea, right? So having said that, the classical cryptography solutions currently in vogue are not secure, no? People are not sitting idle, no? The classical cryptography people, the computer scientists in our CSA departments, for example, are not going to just sit for that day to come, no? They are coming up with better and better protocols and encryption schemes based on even more complex problems, basically. And that's what is known as PQC, or post-quantum cryptography, right? The whole field of post-quantum cryptography comes up with better and better classical cryptography solutions, which become even more difficult to break, even when you have access to a classical, even when you have access to a quantum computer, basically, right? And in parallel, there's also a lot of work on quantum key distribution, where the security of your communication is based on rigorous proofs based on principles of quantum mechanics, right? If I define a photon as some state, for example, and it's very well defined, that single photon, I cannot break it up, right? I'll be talking about this in later part of my talk as well. So when I cannot break up that photon, there's something very fundamental about that single photon. So if I can use those such kind of properties to do quantum communication, then I can guarantee that communication will be secure. And that's the whole field of quantum key distribution, which relies on quantum states of light to do communication, basically. And what is seen is that in the future, it wouldn't be only PQC or quantum. Hybrid solutions are also being thought about, where quantum and post-quantum cryptography would coexist, basically. And that's also a world where we might live in the next 10, 20 years. Some of our communication may exist in this kind of a hybrid format. Something very, very secure would be through the quantum channel. Something which is not as secure, but still under threat to be broken up by a quantum computer, would rely on post-quantum cryptography type solutions, basically. That's the idea, right? So then, do you really have to worry about this? It really depends upon how fast a quantum computer is going to come in to break your schemes, basically, right? So this was a scientist by name Mosca who came up with a rule, right? This is not like Moore's law, but it's just a rule, right? A rule of thumb, basically, which says that how many years is it going to take to break, right? How many years do you want that information to be secure? Let us call that variable to be X, right? It could be varied. No, I already explained. If it's a credit card transaction, X could be a few minutes, basically. And then if it is some other important, very important secrets, it could be in the order of years, basically. So X is a variable which could take different time scales. Y is the time it would take to convert existing classical solutions to quantum secure, right? Whatever means, whether PQC or quantum key distribution, that is Y. How much time would it take to build a quantum computer is the variable on the right hand side, which is, and it's essentially denoted as Z, right? If that time, right, the amount of time it takes to build a quantum computer which can break your codes is shorter than the sum of x and y, then you have to worry. Or in other words, if x plus y is greater than z, then one has to worry about securing that piece of information. Then you have to invest in quantum cryptography solutions or rigorous post-quantum cryptography solutions. Basically, that's the message, right? So it's just a rule of thumb which can be used to evaluate the kind of information you have which you want to secure based on how much effort it would take to convert that information to or make it more secure, and how much effort it would take to break that. Basically, that's the idea, right? There are papers which have been written by Mosca, which is also available, basically, which talks about this in more details, right? So that is the idea, and that's why. So this is essentially motivating to do quantum communication, that the current cryptography solutions may not be secure, that one may have to go to quantum-based solutions. Basically, that's the idea. But then now we are going to take a step back and then look at an even bigger picture of communicating information with quantum states of light, right? So this is not only particular to key distribution. Key distributions are just one aspect to this, right? But you can think of something even more bigger than that, basically, right? If you have quantum computers, no, they're definitely going to come, right? They are already being tested. We hear something or the other coming in the news every other week. Basically, there's a better protocol which has come in, or better quantum computers being built, and so on, right? Eventually, what people would want to do is to interconnect those quantum computers, right? There are better and better quantum sensors which are coming up, which are doing very precise measurements, right? Maybe it may not impact our life immediately, but maybe those precision measurements will be useful to build better MRI machines, for example, or to do precision measurements to understand the fundamental constants, right? A physicist may be interested in these kind of problems, right? So then once these quantum sensors get deployed, no, they have to communicate that information, right? That fragile quantum state of light or quantum state of any particle needs to be communicated, right? That is important, right? You would not want to have them just at remote locations as selected nodes, but they have to somehow exchange information, right? Similarly, quantum key distribution nodes will also be present, right? So then one can think of interconnecting all these to build a quantum internet or a quantum network in the future where all these things will coexist, right? So if you think about maybe 90s, no, where people had their own separate computers, it was very hard to connect to the internet, right? I used to have a modem at home, which used to make all these sounds and then eventually connect, right? So okay, I was happy with the connection, and then it was just if I could connect to an end node, get some information, I was very happy with that. Now that's not sufficient, right? Now we have a lot more devices, mobile devices, iPads, iPhones, everything being connected to the internet, right? Sensors are also being connected to the internet, right? People are doing sensing, right? For whatever application that may be, those also get connected to a sensor network, basically, right? So then you've seen how the Internet of Things, right, and the Internet of all these computers, devices have exploded, right? A similar thing is being envisioned for the quantum space as well, where all these different quantum resources and classical resources will somehow come together in the future, right? Right now, we are probably not at the stage where we are just working on the individual nodes, getting them better and better, basically. But in the future, obviously, there will be communication between them, and that encompasses something even bigger than just doing cryptography, basically. That's the idea. And that's what excites researchers like me, where now I can think about what kind of photonic devices will go into talking between different qubits and so on. And that's where new research problems come in as well, right? So there's been a lot of investment, right? Money being invested in different parts of the world into quantum technologies, which I call as QT in short. For example, US, China, UK, Japan are all the leaders in this space. Even our own Department of Science and Technology has started a QUST initiative in 2019 with a modest investment of about 130 crores, basically. Subsequently, this National Quantum Mission was announced, which is an 8-year project in 2023 with a total outlay of about 6,000 crores, right? So big plans are there to have successful implementations in each of these devices, sectors, basically. Right. Also, another important part of it is the human resource development as well. There are different MTech programs which are being started, right? both in IISc has a QT, right? Quantum Technology MTech program. We have successfully run it for 4 years now, right? Those students get placed in all these startup companies and even well-established companies like Toshiba and so on, in the Bangalore ecosystem, basically, right? So, and some of them go to do advanced research as well. And similar MTech programs are being started in IITs, IISERs, and so on. That one needs manpower, no, trained manpower who can help contribute to advancements in these areas, and that's also happening basically. So this is a very brief glimpse about quantum technologies around the world. What is quantum communication? I've already explained this. Quantum communication is broader than QKD. It involves transmission of quantum states, not just for cryptography, but securely across different kinds of nodes, basically computing resources, sensing resources, communication resources, and so on. And this would eventually help us build a interconnected quantum resource, a quantum internet, or quantum network in the future. Where are we in this scale? So in the top left corner, there is essentially different milestones which are mentioned. What are the different stages of doing quantum networking? Right. The first one or two has to do with quantum key distribution. That's something which is more or less perfect, or I wouldn't say perfect, but then it's reached a much higher level of advancement, right? Where there are boxes commercially being sold, deployed, and so on. There are different nodes, right? For example, as part of National Quantum Mission, there are plans to interconnect from Chennai all the way to Delhi and so on, right? Having multiple nodes and so on. So this is something we know how to do, right? And there's a lot of effort which has gone into developing the right tools and technology for that. But if you look above the first two, no, the rest of them, entanglement generation, we know how to do this in the lab. There are some test demonstrations in field settings, but still it's in very early stage. Then, if you need to store quantum information, I need what are known as quantum memory, right? Where I can store information. That is in a very early stage of research in India, though there's a lot more advancements around the world. Then you may want to do these communication in a fault tolerant scenario where there needs to be error correction codes and all that incorporated. Then one can do computing as well, distributed computing. That would be the eventual goal where there are multiple resources. Then the computational task can be distributed, done, performed across distant parties and so on, which will become very useful for, like, for example, if there are new pharmaceutical drugs being research being going on, it takes lots and lots of effort to figure out what would be the right molecule composition and so on, where such kind of computing resources are envisioned to be required to essentially speed up this process basically. So this is just one example, but a lot of other industrial problems where there is interest in throwing that power of doing quantum computing to the problem at hand and then see what benefit it will bring. Is it better? How much better it is than classical and so on? There's a lot of interest and research, at least in the simulations and the exploratory stage around the world, basically. And once the right hardware comes in, a lot of these will be tested in the hardware as well. Right? So this is briefly what quantum communication is. What are the basic principles of quantum communication? We want to transmit qubit information, and then this has to obey rules of quantum mechanics, right? What are the rules of quantum mechanics? Quantum states can be represented as a superposition in some basis states, right? What are basis states? I'll explain that in my subsequent slides. Quantum states can exist as entangled states with stronger than classical degree of correlation. That's also a very important property of quantum states. I'll also explain this in the subsequent slides, right? And once those states are prepared, nobody knows what those states are until you do a measurement when that state collapses to a particular basis state, right? The measurement basis, whatever you used, it will collapse to that state. And only at that point, you will know what that state was, right? Another important property is that once you prepare these quantum states properly, they cannot be cloned, right? So there is a no cloning theorem which states that if I have a quantum state or a wave function, if I try to clone it, that operation is not possible basically, right? There are proofs for this no cloning theorem which can be found. So I can use this property to do cryptography, because if an eavesdropper is trying to tap into my quantum state being communicated and tries to clone it, right, then he cannot clone it, because the fact that he's tried to clone it, it will perturb that particular state, and Alice and Bob can figure that out basically. That's the idea, right? So then what are the basic carriers of quantum information for communication, right? Here, I'm not talking about computing and other things where different qubit bases are used and all that. But here, I'm going to restrict to communication, and photons are the natural winners if you want to do quantum communication because they already exist in quanta, right? There are discrete packets in which photons exist. So I can use that property. That discrete packet can be called as a single state, which I can use to do communication. Moreover, photons exhibit different degrees of freedom as well. There could be polarization, frequency, wavelength, time of arrival, and so on. All these properties of photons can be leveraged to encode the quantum information. For example, if I take polarization, I can encode in a horizontal basis and a vertical basis, for example. Those form the orthogonal set. And similarly, I can have a 45 and 135. And these two pairs become the non-orthogonal basis I can use to do communication. Similarly, I could find states like early, late, and so on as well in the time domain. Right. Another important property is that photons exhibit wave-particle duality. Right. A single photon can also give rise to some kind of an interference signature. Right. It's not single photon interfering with itself, but then its wave function, when I write it across the system, it will be written in a superposition state that when I do any measurements, the probability of measuring it will show that property of that interference, basically. That's the idea. And it can also exist as particles because that we are familiar. No? Photon, when we talk about photons, we think about photoelectric effect. There are discrete quanta of light which triggers or which can excite the atoms from certain state to the other. All those are known, basically. So particle picture is clear when I talk about photons. Wave picture is often not clear. Right, but then it's the probability. No, it's not the field which undergoes this interference. It's not like an Young's double slit experiment where I'm measuring fields or something like that. But it's like if I repeat the photon measurement multiple times, its probability distribution will follow interference effects basically, and that can be measured. And photon pairs can also be entangled, which make it that much more interesting to do specific communication or sensing experiments as well. Right? So that is the general idea of using photons as your carrier of information to do communication. Um, so there are different kinds of communication protocols which exist. Alice can prepare the states. Bob can do the measurement, which such type of protocols are called prepare and measure type protocols. Then there are protocols where Alice and Bob separately prepare their own states, communicate to a central party called as Eve, for example, or it could be Charlie, right? I'm calling it Eve because it can be the malicious party even. The malicious party would know only the result of the measurement, but they don't know what the states which Alice and Bob prepared, basically. Right? So where this thing comes in useful, no? If I am trying to do point-to-point communication, then the prepare and measure type protocols are very useful. If I'm trying to set up a network topology, then this kind of Alice communicating to Eve, Bob communicating to Eve, such kind of star topology comes in very useful. Now I can build many such nodes, no? Not only restricting to Alice and Bob, I can add more nodes. I can build a network with this basically. So that's where these kind of entanglement-based schemes become very useful. It naturally lends itself to set up a network basically. That's the idea. Right? There are a bit more details, but I'll skip them in the interest of time. But very broadly, I classify these kind of nodes or implementations as point-to-point, which we call as prepare and measure, or two parties talking to a middle party, which we call, for example, a popular way to do this is by using entanglement as a resource to do the distribution. Right. So then I'll move on quickly to talking briefly about some of the communication hardware which is used. This is what I want to talk about, right? This is where the heart of it is. A lot of quantum optics is involved here. I'm going to skip a lot of the math and then explain to you very briefly what are the different components you would require if you want to build a quantum communication system, right? There are light sources which are required. Quantum light sources. And in particular, I'll talk about single photon sources, entangled photon sources, and something which is known as weak coherent source as well. Right? Subsequently, I'll talk about qubit selection or basis selection, where you need some kind of random numbers which are being generated. High quality random numbers. These are not pseudo random numbers you generate in MATLAB, for example. These are very high quality random numbers generated by some physical process that we call as QRNG, quantum random number generator. Then we will talk about qubit encoding. How will you do qubit encoding using intensity and phase modulators? Or even polarization modulators. I'll be able to set the state, right? Whatever degrees of freedom I talked about earlier, I have access to them. I have to encode that qubit information. Qubit 0 is mapped to horizontal photon. Qubit 1 mapped to vertical photon and so on. That encoding happens using what is known as a modulator device. right? Then when you talk about quantum channels, what is the channel across which one does communication? You can have optical fibers as a medium to do communication. You can also have free space as a medium to do communication. Both are of interest. There's a lot of advancement which has happened recently in both these channels to do quantum communication. Then when you want to do quantum state detection, you need very good detectors, high sensitivity detectors capable of detecting single photon, single or few photons at a time, right? I don't want that detector to be overwhelmed by background, that I want to detect a single photon only, right? So then I need what are known as avalanche detectors, which have a built-in gain mechanism, which I use. Or recently, there's been interest in superconducting single photon detectors as well to do the detection. So next few slides, I'll quickly talk about some of these essentially the hardware components which go into building a quantum communication link, basically. Right. So before we move on to these devices, it's also important to understand the concept of qubit. Right. You're probably aware of the classical bits. No, I'm sure you've done a computer science course where you would learn about bit zero, bit one. If I talk about digital communication, I would encode bit zero by 0 volts, bit one with 5 volts, or even if it's a TTL logic, or something even lower if it has to be CMOS compatible. I would go with 3 volts or 1 volt even is often used to define your bit one, basically, right? Extending that concept, no, I can represent what are known as qubits, which are denoted in this ket notation. The ket 0 denotes my qubit 0, ket 1 denotes a qubit 1. And what is unique about doing this quantum encoding is that I will also be able to generate states which are in a superposition, right? It could be alpha times ket 0 plus beta times ket 1. And these are complex wave functions that I can also have a relative phase between 0 and 1, right? It's very easy to see this if I talk about polarization states of light, right? So if you look in my next bullet point, no, at the bottom, I've written in the polarization basis, my qubit 0 can be a vertical photon denoted by the vertical arrow. Qubit 1 can be a horizontal photon denoted by this horizontal arrow, right? There's no reason why I need to have only these two. I can have superpositions of that also, right? So in this case, I show a 45-degree polarized light where 50% of the time it's in vertical state, 50% of the time it's in a horizontal state. There's no relative phase difference between them. Or I could have a 135-degree photon, polarized photon. The only difference is that it's pi out of phase between the H and V polarization state, basically, right? This is just one example. No, I can create such kind of states. Many such kind of states can be prepared. The way they are represented by using states on the surface of a sphere, which is called as this Poincare sphere, right? A lot of this comes from classical optics, where my pure states 0 and 1 form the North Pole and South Pole, basically. And then my mixed states, which I showed here, no, the H and the 45-degree and 135-degree, those will form states in the equator, right? These are of essentially 50-50 probability, and then they could have any relative phase between them, and they form states in the equator. If they have pi by 2 or 3 pi by 2, I'll call them as light left circular and right circularly polarized light. Any other state, no, where it could be 30% probability of finding H, 70% probability of finding V, no, those kind of states with a relative phase between H and V, those form states anywhere in the sphere, basically. And that's where you can represent, basically. This kind of a Poincare sphere is essentially a very good tool to visualize these kind of states, basically. Right? No reason why it should be restricted only to polarization. I can also think about time bit, right? If I encode pulses in time, I could have an early pulse and a late pulse, right? What you see here in the 2D QKD schematic is that there's a pulse shown in blue, there's an early pulse, there's a late pulse. I could have a superposition between them also with a relative phase, right? With different uh, intensities, right? So then what will happen is that I can create 50-50, I can create 45-55, whatever percentage. The percentages are really probability. When I write them as wave functions, it's the square root of them, no, which forms the the amplitude, right? Probability amplitude is what is written when I write the wave function, and that's why you see a square root in 2 in front in some of these representations. So you can see that these are two examples where the qubit can be encoded using photons, using polarization or time, right? Those are fairly useful states. And then I can correspondingly detect them by using suitable polarizers to project them onto suitable measurement bases, basically. This is not the only ones. I can think about spatial modes, orbital angular momentum modes. Lot of other degrees of freedom of photons are there, which can be used to encode such kind of qubits, basically, right? So then there is what is known as single photon, which is a well-behaved packet of just energy equal to 1 h nu, right? If you see, no, if we have light in this in a room, for example, there are many photons. There are billions of photons, for example. Many photons are there in this room. But then if I have the capability to isolate only one photon wave packet, then that is what is known as a single photon state, right? These are very powerful states because I cannot divide a single photon, right? I give this example where if I go and take a classical object like an apple, I cut it, then I can get two halves, no? But if I take a quantum object like a single photon, and the cutting operation is equivalent to sending it through a beam splitter, then what will happen is that photon will either be transmitted or be reflected. I cannot get it 50-50, basically. That's the idea, right? So this is a very powerful concept which can be used for doing secure communication. Obviously, one detector can be Eve who is trying to eavesdrop. So if the photon goes to eavesdropper, it obviously doesn't go to Bob. That photon is lost, basically. So this essentially guarantees security because of the fact that the single photon is an indivisible entity. Similarly, I can use this concept for random number generation as well, right? If that photon goes to detector D0, I call it bit 0. If the photon goes to detector D1, I call it bit 1, right? So then I don't know a priori where it will go, but randomly it will go into path 0 or path 1, right? That property also can be leveraged to do quantum random number generation as well, right? So you can see that if I have the capability to generate single photons, it seems to be a very powerful entity that its basic characteristics can be used to do quantum communication, random number generation, and so on, right? So, but then how do you generate it is another separate lecture in itself. I'm not going to go into it. People are figuring out ways in which they can generate one photon at a time, basically, right? There are ways to do this efficiently. Again, yeah. Then moving on to single photon, no, I just described. You can have what are known as quantum dot emitters, 2D materials, nitrogen vacancies in diamond. Lot of different material systems are there. Where I'm sure if you have done the semiconductor course, no, you would have learned about density of state. Right, it's an important concept in if you learn basic semiconductors. Right, if I restrict the density of state to be exactly like one state, no, if I fill that state, then the second electron cannot go and fill that state, right? So then that electron has to transition down, and then when it transitions down, one electron hole combining will give rise to only one photon, right? That's the way I guarantee that it's a single photon state, right? By restricting the density of states in that material. So all these systems I'm showing here are examples of low dimensional systems where the density of states is restricted, basically. That property can be used to generate single photon, one photon at a time. Moving on to the second class are what are known as weak coherent sources, right? These are like substitutes. These are surrogates for single photon sources. You don't have a single photon source, then I make use of a regular laser source or a lamp source, light bulb, for example. I attenuate it. I make it weak as weak as possible, that on an average, it will have one photon at a time. But bear in mind that the statistics they follow is very different than a single photon source. In a single photon source, I can guarantee that there will be one photon at a time reliably, right? It's only a one photon wave packet at any point in time. The photon number fluctuation is zero, basically. The variance in the photon number is zero. Mean is always one, for example. But I cannot guarantee that in these weak coherent sources, that what it means is that at any point in time when I do a measurement, it could be zero photons, which are called as vacuum states. It could be one photon, two photons, three photons, and so on. And it in fact follows what is known as a Poisson distribution. Because short to short, the quantum nature of the emission process ensures that you get a Poisson distributed photon number, right? And the fact that I'm attenuating it means that at low and low mean photon number, on an average, right? I restrict the multi-photon events that I will have 0, 1, 2, such kind of photon events only, right? And that's why they are called as weak coherent sources. They are only surrogates, right? They are not really the real quantum sources, but then they are substitutes, right? And they essentially help in simplifying my quantum communication link. But then one has to be aware of what kind of restrictions they have also, right? The fact that they have multi-photons also, there's a finite chance that they'll give multi-photon means that eavesdropper can tap into that information. And that essentially means that the communication may not be secure, right? So that those are things which need to be taken into account when one implements a quantum key distribution system, making use of weak coherent sources, basically, right? But these sources have been very popular to do quantum communication, though they are not really quantum sources. They are more classical sources, but they are used as a good substitute, basically. So the last concept I would like to talk about in the light source is this concept of entangled states, right? As I told you before, they have non-classical correlations. So what does it mean? It cannot be factorized into wave functions of the individual particles, right? So for example, if you can write a bipartite, a two-party state, the subscript 1 and 2 denote the two parties, right? Then if the first party is 0 qubit, the second party is also 0 qubit, right? They are highly positively correlated. Or if the first party is 1 qubit, the second party is also 1 qubit, right? At any point in time, I don't know a priori what state it is, right? But then, right, when I do a measurement, if party one state collapses to 0, automatically I know that party two state is also 0, right? A good analogy would be like if you go to a lecture, no, if you're going to your classes, then you and your friend, no, you don't a priori decide what color dress to wear, right? But then you think of a situation where, for example, if you wear a white dress, for example, your friend wears a black dress, or vice versa, right? This is the quantum nature where a priori I don't know, right? But then once I see you wearing a white dress, I automatically know that your friend is wearing a black dress, right? Before measurement, I didn't know that. But once I measured, no, with my eye, I look at you, I see the white dress, then I know automatically that your friend should have also worn a would have worn a black dress. Right? That shows strong negative correlation. Those are states which are shown in the bottom. The psi plus minus states are the ones which show negative correlation. Right? How this is useful is for doing communication. Exactly like what I described, the white and black analogy can be extended to doing communication as well. If I do a measurement on one, automatically I know what that other person would have received as well, right? So that is a very important or very powerful property which is leveraged to do communication. Not just communication, there are a lot of other things which are being proposed. One can do quantum sensing, lidar, imaging as well. The fact that they are strongly correlated can be leveraged for doing sensing better than what a classical implementation would do, basically. How are these systems implemented? So even before I get there, so this is a thought experiment with Schrodinger, the famous quantum mechanics scientist who came up with. This is what is known as the Schrodinger cat thought experiment, where you think of a room in which a cat is sitting, and then there is a cyanide capsule as well, right? Then what happens is that if essentially there's a Geiger measurement device and an atom which is present here. If the atom decays and then it triggers the Geiger counter, it will break the cyanide capsule and that cyanide will be exposed in the room and then the cat will be dead, basically, right? Or if the atom has not transitioned to that state, then the cat is alive, right? So then, right, I don't open this room, but then what happens is that you want to write down the state, then the cat is alive, the state is in 1, right, the upper state, for example, or the cat is dead and the state is in 2, the lower state, for example, right? So this is an example of that entangled state, right? Such strong correlations in two particle systems exist in microscopic world, right? This is just a thought experiment. In macroscopic world, such correlations get lost due to decoherence, right? You don't maintain that coherence long enough. Photons are particles which can maintain coherence long enough that I can measure that and then do something useful with that. But in the macroscopic world, I will not be able to do this. But it's not restricted only to two, right? I can extend that to 3, 4, 5 as well, where things get even more interesting. I can distribute those 4 or 5 states, right? The 4-party state or 5-party state to 5 different parties, do measurements. Then 5 parties can simultaneously communicate, right? So a lot of interesting things can be done if one can prepare such kind of states. 2 or 3 is doable. Beyond that, things get very difficult to prepare in these microscopic systems, basically. But this is just a thought experiment which is often used. But really, how do you prepare them? A bit more detail. So this is where our expertise in nonlinear optics comes in. We make use of what are known as nonlinear crystals, where if I send in an input pump, it spontaneously splits into signal and idler, right? These processes are designed in a way that there is energy conservation. So the sum of the energy of the signal and idler is equal to that of the pump. There's also some specific polarization conservation also, which these photons have to achieve. So what happens is that at the point of generation, I don't know what the polarization states are, right? I prepare my experiment in a way that I don't know what the state of the signal and idler are, but I prepare them in this kind of a superposition state. If the signal is H, idler is V, for example, polarization, or vice versa. Such kind of experiments can be planned out. For example, this is one popular experiment where if you start with a nonlinear crystal, the output essentially follows these ring patterns in the intersection points of these rings where you get these polarization correlated photons and so on. Right? If you're interested, there are references at the end, but this is just to essentially provoke your interest that there are very interesting ways in which these nonlinear processes can be leveraged to generate photon pairs and then use them subsequently for applications, basically. We ourselves in my lab, we are trying to work on quantum imaging experiments where we would like to generate these kind of correlated photon pairs, use them to do imaging, right? Both linear and non-linear type imaging is something we are exploring currently. Right? There are different entanglement schemes and all that. I'll skip. QRNG, I already mentioned. You are essentially leveraging randomness in your quantum process. One such one is this randomness in the single photon, right? Randomness in the where the single photon gets split, right? Where which path information is not known, and that's where the randomness comes in, basically, right? These kind of sources are truly random, right? If an eavesdropper cannot know the pattern, right? It's not like a pseudo-random numbers generated with shift registers, where if you know few numbers, you will be able to predict what happens. These are truly random, and that's why there is interest in using them, right? If you're building a QKD system, obviously you want these kind of sources rather than pseudo-random numbers. You don't want to compromise security because of the random numbers you use, right? And that's where there is interest in using such kind of sources to do communication. Right? What is the quantum channel which is used? I'll very quickly talk about this. Fibers, this is just classical communication. We borrow things from classical communication. There are a lot of long haul fibers which are used to do continent level communication. For example, China demonstrated QKD from Beijing to Shanghai, using like 20 odd nodes which are connected to build a prepare and measure setup. So these things are getting very popular. A lot of the experiments we do in the lab also we have to use these kind of fiber spools, right, to show that they can indeed be done with real fiber spools. We also do experiments across campus. In IISc, we have some links which we are testing across different departments to show that they are in fact field deployable. They are not only lab type experiments. You can also deploy them over the institute and also to campus and then do these kind of communication experiments. Right? Then taking it to the next level is to do satellite communication, where as you start increasing the lengths of these optical fibers, losses become prohibitively large, right? So one way to avoid such high losses is to use free space as the medium to do communication. Again, China has deployed a Messier satellite, which has been used to do quantum secure communication between continents even. They demonstrated I think video transmission between a ground station in China and another ground station in Austria, basically. Right. So a lot of interesting experiments have come up. India also, there's a lot of interest in implementing this. ISRO has been interested in implementing free space satellite communication as well. Right? Single photon detectors, I already mentioned. You need very high sensitivity detectors. The typical detectors which are used are these avalanche photo detectors, where the avalanche multiplication in a reverse bias diode is what is used for doing used for photon detection and subsequent electron amplification. Similarly, superconducting detectors are also the new detectors in the which are available, where essentially the detector is kept in a superconducting state nominally, and when photon is incident, it transitions from superconducting to a highly conductive state, highly resistive state, And that property is what is being leveraged to detect the photon, basically. So initially it's cooled down to its superconducting state. So it's like a niobium nitride or one of these superconducting materials in a nanowire form. And then that nanowire, when light is incident, it transitions from the superconducting to insulating state. That whatever current is there in the circuit is read out through a load resistance, basically. Very simple circuits, but very powerful device, basically. Right. So then there are a lot of properties one can look at and all that, which I will skip. But very briefly explaining, there's a lot of research happening in building these kind of superconducting detectors, how to operate them at higher and higher temperatures as well, how to integrate them on a chip. Right, these require separate high degree of cooling, basically, which makes it prohibitively difficult if you want to deploy them on the field and so on. So there's a lot of research happening in higher temperature superconductors which can be used. Also, how do I integrate them on a chip so that the cooling requirements may possibly go down as well? Right. So moving on to the last or almost the last part of my talk, I'll briefly talk about the quantum communication or cryptography protocols. One of the popular ones is what is known as this BB84 protocol. The original proposal was actually, in fact, done by Bernard and Bresard here in Bangalore at a conference in Bangalore. So we have some connection to that. The original proposal was in a paper where they proposed that we'll make use of single photon states which cannot be eavesdropped. No, that's why the assumptions, there are no assumptions there. I have a single photon state, which I know that it cannot be split further. Then I encode information in the polarization basis. I use horizontal, vertical, or 45, 135 to do the encoding. And similarly, Bob at the other end does basis selection, either the HV, the rectilinear basis, or the diagonal, anti-diagonal basis is what is used for detection. Right. So then if they both chose the right basis to do communication, then assuming there is no noise or anything which is affecting that qubit, then whatever Alice would have transmitted would have been received by Bob, basically. Then in the presence of noise, those information can get corrupted. Or if there is an eavesdropper who is tapping and then resending, that would also corrupt, and then the errors would go higher, basically. So based on the errors, I'll be able to predict whether there has been an eavesdropping or not, basically. Otherwise, these kind of protocols guarantee security based on principles of quantum mechanics rather than having computational assumptions, basically. And that's where things become much more tighter. No? The security proofs become tighter because it's guaranteed by physical principles rather than assumptions. Right? That's very important to understand. Post quantum, no, then Alice and Bob agree on what basis, no, they can try to reconcile, try to make sure that they use the right basis to do communication, and that operation is called as shifting. Right, then there could be errors which are introduced, so they want to eliminate errors, so that's where all these error correction and all come in. And then Eve could have tapped into some information because of whatever reasons, non-ideality in your implementation or whatever. You want to minimize Eve's information, and that's where what is known as this privacy amplification step comes in useful, where the privacy amplification is used to ensure that Alice and Bob have the same piece of key with no information or very little information which Eve has, basically. That's the idea of doing privacy amplification. So it's not only the quantum communication which is important, but all these post-processing steps, which are classical, is also important in successfully implementing one of these quantum key distribution schemes. Right? So the first experimental report was almost 8 years later in 1992. It occurred in a journal of cryptography. And this is what the picture which is taken from their paper. It's very crude, no? It's a lab level implementation. LEDs were used. Obviously, LED is probably a weak, it's not even a coherent source. It's a weak thermal source, basically, which was used. The communication happened through a 30 centimeter length communication channel. Detection happened. The qubits were encoded in polarization basis, HV, diagonal, anti-diagonal, and similarly detected in similar bases, basically. Right? I'll skip a lot of the details, but just the key, 10 minutes of communication was done. About 77 lakh, 71 lakh, 7 lakh 15,000 pulses were transmitted across 10 minutes of communication. And at the end, they were left with about 754 useful bits they can call as secure after doing all the post-processing. So roughly, they were able to transmit 1 bit per second. Right? That was the state of the art in 92. Subsequently, a lot of effort has gone into improving on this. Nowadays, the best results are about 1 megabit per second secure key communication across tens of kilometers of length. Right? So a lot of advancements have been gone. into getting better and better devices which can be used to encode, detect, leveraging a lot of advancement in fiber optics to set up these kind of communication links. Right. So then I also talked about entanglement-based protocols. A source of entanglement, no, this is what is known as this Eckart 91 protocol, came up by the scientist Eckart in the year 91, where 1991. The source S is where the entangled photons are produced. One of that photon is distributed to Alice in the left side. The other one is distributed to Bob on the right side. Then you do measurements using beam splitters, right? And then once Alice detects a certain state, no, since they are entangled, Alice would automatically know what Bob would have received, right? That's the powerfulness of this protocol. The source can be an eavesdropper even preparing these states as long as it's quantum certified. No, there are ways to certify that it's essentially entangled. Once that is guaranteed, then Alice and Bob can do communication by just detecting. If Alice detects one, automatically they would know what Bob would have received. Basically, that's the idea. Okay, there are a bit more details I'll skip in the interest of time. I'll quickly go on to what is the state of the art in doing quantum communication. There's interest in doing getting to higher and higher key rates, right? So the state of the art is more about 10 Mbps is what I know of over distances of about 300 kilometers. Then there is interest in extending to longer and longer distances. In fibers, the lengths have been as close to about 1,000 kilometers has been demonstrated by more advancements in protocols. There's something which is known as twin field QKD, which is being used. There's also interest in implementing them in free space, which is the popular one is the Chinese Vicious satellite. Well, there's also interest in India as well. ISRO has been looking into that. There's interest in miniaturizing these into chip scale, right? If I can make the transmitters chip scale, then there is a path forward to building many such nodes to build a quantum network, right? So even my lab, we work on this photonic integration to build chip scale transmitters, integrating them with electronics on the board to realize QKD transmitters, basically. And eventually, once we are able to demonstrate some of these photonic hardware, then one could envision or think about building some of the requirements for a quantum internet, right? Interconnected quantum resources like we talked about. And you can also think about building quantum repeaters and also swapping entanglement between different resources, such that if I have some qubit or some state which is prepared remotely, that could be transferred to some other state by doing photonic measurements or optical measurements, right? So there are a lot of interest in doing these or demonstrating some of these things in India as well, so that eventually we'll be able to incorporate them in a quantum internet. There are many companies who sell boxes capable of doing quantum communication or quantum key distribution of particular. There are also there are companies like ID Quantic in Switzerland, Q-Tools, I believe, in Germany, and QNew Labs is the one in Bangalore who also work on. So these are some of the specifications from their data sheets. You can communicate qubits at 128 kbps. So if you compare with classical communication, no, my Wi-Fi access point may be able to nowadays provide even 1 Gbps kind of rate, right? So we are far away. But then what this guarantees is security, unparalleled security when compared to other schemes. So if you really care about security, then you will be willing to invest in this and take the hit in terms of key rate to do secure communication, right? That's the idea. Right? There are field deployments as well around the world. These are few examples. As I told you, as part of National Quantum Mission, I'm part of a consortium. We are looking to interconnect between Chennai to Delhi at some point in time using multiple nodes to set up the communication. Right? There have been many demonstrators in India. A few of them, maybe this is almost a couple of years old, where there's been interest in fiber. You know, DRDO has been looking at 100 kilometers of fiber, trying to do QKD and so on. There's also interest in free space links, though the lengths are much shorter. In them, key rates are also shorter, but a lot of promising results are coming up in the lab, which will be tested in the field as well shortly. Right. So I'll stop here. I'm almost maybe past an hour also. I'll just conclude saying quantum communication technology aims to establish reliable communication between quantum resources, right? Transmitting qubits between two or multiple nodes. QKD is a particular subset of quantum communication which aims to guarantee secure communication. While quantum communication more generally aims to do reliable qubit transmission, QKD aims to do very secure communication where key rates are still not as good as classical, but still there are ways forward, right? This is one of the most mature quantum technologies. The four sectors I told you, communication, computing, sensing, materials, and so on. The other ones are much more at the earlier stage. Quantum computing or quantum key distribution is at a much more advanced stage, basically, right? What are the cutting edge problems? How to build high efficiency, high performance devices? How to do long distance, high data rate communication? These are problems we are also looking at. How to push the data rates using high dimensional encoding? How to miniaturize them using photonic integration? How to generate entanglement on a chip, distribute it for communication, imaging applications? All that is of interest, basically. An ultimate goal, if you are able to succeed in this, eventually to interconnect these devices to build a quantum internet. Right? So I'll stop here. Some of the take-home messages I showed, I'll flash it again. What is cryptography? What is the need for doing quantum communication? What are qubits? What are single photons, entangled states? How to do QKD, and some of the ideas on state-of-the-art QKD. So I hope I have touched upon some of these topics, and hope you are able to get some idea about about some of these concepts, basically. Right? These are the useful references. I hope this will be recorded. You will have access to this. Thank you, and I'll be happy to take any questions. We are also looking for motivated MTech research students, PhD students, even project students as well. If you're interested in short term, maybe jointly with your university professors, do reach out. We're always looking for interested, brilliant students. I'm sure NIT Trichy has lots of them, so that's why I'm advertising here. If you're interested in our programs as well, check out the admissions webpage. You will find a lot more information about the different programs, what are the requirements and all that. So, in fact, the NIT, since they are government funded institutions, I think students with GPA above 8 can directly apply without gate as well. So there are some incentives provided for the CFTI students as well. So do look out for those things. Right? Okay, I'll stop here. I'll be happy to take any questions you may have. Thank you.
Thank you, sir, for this session on quantum communication. So we would like to do a quick Q&A session with you. If
Yes. Any questions? Go ahead.
So first, I would like to ask, like, for students who are exploring technical fields like optics or engineering, what foundational topics or skills would you recommend focusing on during their studies for
So
this
I think
topic?
from what you learn in undergrad, no, having a good background in communications is good. If you since most of you are from the ECE stream, no, I can say that having a good understanding of communications is good. But even if I go one step before that, some of the math topics, no, which are very useful, it's good to know linear algebra, no, and then it's good to know probability, right? Those two topics are very useful if you are doing any of these courses, especially quantum. There's a lot of linear algebra which is involved, right? If you have a strong background in these two maths topics, and even to some extent if you know differential equations, that will be useful more for understanding electromagnetics, basically. So having a good math foundation or refreshing your skills is useful. Then when you go on to the basic top, the core courses you learn, definitely the communications, digital or analog, or whatever communication course you are learning, that is useful. Signal processing course is useful. Electromagnetics, no, EM theory, that is also very useful. Then semiconductors, solid. You may learn about semiconductors, not just MOS, CMOS, and BJT and building circuits, no, not at that level, right? But even how a diode works, what are the basics of semiconductors. If you are so the first part of your course may cover that those are extremely useful topics. You will learn something about quantum mechanics or the basic principles of quantum mechanics being applied, right? So those things I would definitely emphasize on. Basic math and some of these core courses will give you a strong foundation if you want to pick up more advanced topics in some of these areas I described.
Okay, thank you, sir. So also, what I wanted to ask, see, what inspired you to pursue a career in advanced research, and how has your journey evolved over the years?
Well, I got interested in photonics because I accidentally started doing a course in fiber optics when I was in undergrad in Brits Pilani. And then I got really interested because the way these photons propagate and how the device works, if you start learning it at the microscopic level, that was really fascinating, right? So then I wanted to work on basic devices. Basically, I was not a systems person. I didn't build any quantum communication system or anything at that point in time. I didn't know anything there. But then I got an idea that maybe I should work on some devices, right, where one can visually at least get a picture of how the device works, and then based on that understand its operation. No, so like a ground up view, you understand the basic device, its operation, where it could be used, and that's where the application comes in, and maybe demonstrate some proof of concept applications, right? That was my interest. And thankfully when I went to my graduate studies, I got an opportunity to work in some of these device projects, basically working in nonlinear optics in silicon as the medium, where the emphasis was on basic nonlinear optics. So I got an idea about how these devices work, the basic operation, then demonstrating proof of concepts, and that was really useful. That really shaped the things I did subsequently, where the postdoc I did in nonlinear microscopy helped. Like everything had a thread where we were trying to do this basic device operation and from there application. And that's what really motivated. And we still continue to do that in my research lab. One thread of my lab does work on basic nonlinear optics. Another thread has gone into more systems level work on free space communication, VLC type communication, quantum communication, and so on. But yeah, that's what kind of motivated me to pursue research in some of the topics I did.
And sir, during your research or your career, did you face any significant challenge and how did you overcome it? Because our students would love to know that.
Thankfully, I was blessed with having good advisors. Right, they were very kind to me. Both my undergrad, whoever I did projects, were kind enough to give reco letters, which helped me move on to the graduate schools I went to. And then the graduate PhD advisors and all were very extremely professional and kind. Because often I hear horror stories like when international students go abroad, no, some of them don't get treated well or whatever that reason may be, right? So I was not, thankfully I was not exposed to that kind of thing, where my advisor was extremely kind, careful, taking care of the students, right? So that was very helpful, I think. So and then subsequently my postdoc advisor, since he came from Europe, he had a very different work culture, which I also enjoyed working. But then it was all very rewarding experience with me. In terms of challenges, I would say, uh, like I have done few transitions from industry to academia and so on. Like I was in a startup company after my PhD. Then I moved to postdoc, and then I moved back to a more well-established company. Then came back to a faculty position. So these kind of transitions, no, you kind of the challenge there is that in an industry you are interested in what product you build, what will bring you money, no, that profits and those kind of things are what one is worried about. Right? Basic research is something one doesn't care about. Writing papers is something one doesn't care about. So then, if you're transitioning to academia, what matters is doing good quality research, doing cutting edge research, writing papers. That's what counts basically, right? If you do technology transfer, that also counts these days. I'm not saying that doesn't count, but then like that, primarily what matters is to do cutting edge research, to do our day to day life basically. So that transition often poses a challenge because sometimes you're kind of get into this cozy spot where okay, you get enough salary, you're happy with the work you do, that to motivate yourself to transition to the next thing, to do research, to that could become challenging. But then yeah, one has to somehow figure out a way to do this. The other challenge is always time management. No, you have multiple things which will be at you. No, you have to do courses, do research, especially when some of you may take up graduate studies. So those things will become important. So how do you do that? How do you do time management? Those things become important as well. Right?
Sir, since you were graced with great advice from everyone that you worked with, what is one advice that you would give to the students who are looking to identify impactful research areas or projects in any technical field?
So one thing is to go with your gut feeling. Like often, if there could be a lot of noise from the people around you, no, saying that area is going nowhere, or don't pursue this, right? Or it may be like, oh, if you're doing research, then you will not earn money. right? Such kind of the comments come from people, especially close family, who really care about you and your future, no? So that often happens, right? Which is good only. I'm not saying that is bad, but then at some point in time, if you think that area is of interest and you are really passionate in working in something, you should put your 100% effort and work in that particular area, and then make it successful, whatever it takes, right? If you if it fails also, it's okay. That learning experience you should take, and then move on to whatever is interesting at that point in time, right? So that is what I think you should eventually choose areas to work on which is of interest to you, and then what you find is interesting, where you don't feel the thing as like, oh, every day I have to get up and go to work and those kind of things. If you right and you are really passionate in doing things, then do definitely pursue whatever that may be. It may be biology, it may be art, it may be science writing, whatever that may be. No, you should pursue that and make it successful. That's what I would say.
There are a lot of students looking into going in research. So, what qualities do you think are crucial for students to succeed in research and innovation?
You have to be um, you have to have the drive yourself, right? Even in research, no, what I have noticed is that there are advisors who are micromanaged, right? Let's exclude them. But then if you have PhD guides, no, they what they will do is like they will identify topics, right? And then give that topic, no, they hire you to work in a specific project. There might be senior students who will be along with you, or senior or postdocs who will be along with you. So you have to develop the right work culture to learn, right? You have to. There is no guidance. There won't be lectures, right? There won't be exam, right? The exam comes in at the end where you produce a good quality research paper or good quality research which has impact, right? So you have to train yourself, right? That motivation, you have to have that self motivation to learn areas. I'm sure there are people who can help you out. There will be senior students who can help. You can talk to other faculty, right? So that you should not have the hesitancy to not learn. And then if you don't like that area you are assigned, also you should have the courage to go and talk to the person, your faculty, and then find something you really like to work on, right? And then you should own that problem, and then be put your 100% effort to really be successful in that. Learn whatever it takes to do that, be it simulation, be it fabrication, be it testing, right? That ownership, if you have, no, you will be successful wherever you go. You will take up any problem, and then you will those are the skills you are looking for in doing research, no? Your research problem, maybe after 5 years after you graduate, nobody will care about it, but then that thinking process and whatever you have learned down the line is what really matters. And then you have to train yourself to do that, right? Often, like companies like Intel, no, they used to hire PhDs in some areas, English or humanities even. The reason being that they won't give up, no, they will stick to a problem and make it successful. And those are the skills which are really required, basically, right? And one has to train, right? That would be the advice I would give students.
Okay, thank you, sir. And sir, in this field, like, do you see any recent technological and advancements shaping industries such as healthcare, communication, or imaging?
Definitely, yeah. The quantum sensing, no, there is interest in applying quantum sensing to build better imaging systems, which will help us detect small changes in biological samples, be it tissues, cell cultures, and all that, right? Though a lot of this is in still pie in the sky kind of ideas, which are proof of concepts are being tested out. But that's where the future should be, I think. So definitely in all these medical fields, like if we can build a quantum imaging or quantum sensing system, if it can help in detecting a disease early, there's a lot of impact for that, and people are exploring that. Or can I do better sensitivity imaging? There will be a lot of noise in your image. Can I pick out things, features, or particular targets which are hard to pick out? So that is of interest. In the area of communication, there's interest in doing secure communication, as I said. Quantum internet, I talk many, I think I use the quantum internet word maybe 50 times in my talk. And so there is a lot of interest. That's where the future of quantum communication is heading, I think. Um, yeah, yeah.
Sir, one last question. Like, one last question. So during your research, did you have any like breakthrough project or research finding from your career that could inspire our students?
So I would maybe say one thing which we have recently worked on in the last couple of years. One of my PhD student had worked on this. So what we have been trying to do is wavelength conversion. No? If you have some image in some wavelength, I want to convert it to a different wavelength, right? Why is this important, right? If you think of it, no, we don't even think about this too much. Like you have a cell phone, right? Cell phones, we take pictures, no? The camera there is a silicon sensor that has its own. I'm able to detect my visible image, no, the what I see everyday life I'm able to detect. But if I go slightly longer, no, above the if I send in a photon of band gap which is below of energy which is below the band gap, that silicon sensors will stop working at that point in time, right? But if you think about how much investment has gone into the silicon industry, no, sensors, these kind of silicon sensors are ubiquitous, right? So then if I have some image, for example, in the infrared, right, I'm getting some chemical signature or some gas signature, no, there's a gas leak. I'll be able to sense and acquire an image in the infrared which is sensitive to that particular gas, but I would want to still use my silicon sensor to do the detection, right? So then I would interface them by using what is known as a wavelength converter, which will convert the image from the infrared to the visible, for example. So we recently worked on a concept where I'll be able to build these nonlinear mirrors. It's based on a nonlinear frequency conversion process. That mirror will essentially reflect the infrared, but when it's reflected, it will convert it to the visible, right? Then I can use a silicon sensor to do detection. We recently demonstrated this. It got covered in Hindu and a lot of other newspapers as well. So that was one area where we are trying to advance and trying to see how to take it forward, how to do low light level imaging, how to improve the sensitivity of these devices and all that, which I think is an impactful area which we are trying to contribute to.
Thank you, sir, for your enlightening lecture and for sharing your perspectives and valuable insights with us. Your insights, knowledge, and experience have broadened our understanding of the field. We are grateful for the time and effort you dedicated to sharing your expertise. Oh, we have some questions in the chat box.
The first question can I take? How is India
Yeah, yeah.
progressing in quantum communication research? And are there any key projects or collaborations you are excited about? How is India progressing in quantum communication? There are a lot of research groups who work in the area of quantum communications, hardware side, and also algorithm. Algorithms we implement or proposing new protocols, proving security of existing protocols. There are many, many groups who are working on it for many years, right? We are way advanced in the theory side of things. But where we are lacking is the hardware, but things are changing, right? With the first DSC project on quantum QUST, quantum science and technology, there was a lot of funding injected into this area. We have made good advances in setting up quantum communication links, both in the lab and the field. Now, there are other agencies, DRDO, MIT, a lot of them are also funding work in this space. With the next national quantum mission, we would like to take this further, not just a lab level demo or a small field level demo, but take it to interconnecting cities or interconnecting between, for the one I told you is between Chennai and Delhi. No, that's the ultimate goal. Thousands of kilometers will I be able to interconnect and do secure communication is something we are excited about, right? And there are a lot of groups which are involved. So there's a lot of collaborations happening. IITs, IISc, a lot of labs are involved in setting up such kind of system, basically. So quantum communication. So if you look at the National Quantum Mission document, no, there is something which is publicly available. There are key objectives which are mentioned. So a lot of the projects have to comply to that basically. And then the quantum communication one is dealing with thousands of kilometers of communication with high secret key rate, right? At least a megabit per second, low bit error rates. There are some specifications which are given. Building quantum repeaters, quantum end nodes, a lot of things towards realizing a quantum network basically. So you can look at that document. It's already available in public. And we are trying to meet some of those objectives by our consortium and so on. A lot of effort is being proposed. A lot of exciting things is happening in India, I think. and a lot of manpower is required. So students like you who are interested in these areas should pursue this either through projects, through MTech or PhDs in India and abroad, and also come back to India and then set up your labs and so on. Definitely, we need a lot of good manpower in this area. So the next question I see: how is life as a professor, sir, and how to become a professor? How is life as a professor? I don't know. So, as you know, a professor should teach, right? That is one of the primary goals in a professor's career. We have to advise, guide students also. We get MTech students, PhD students, project students, and all that. We have to guide them. We are also have to, as we guide them, we are also supposed to do unique research, novel research, cutting edge research needs to be done. It needs to be communicated through papers, forums like this, conferences, right? So a professor's job is multifaceted. No, we are supposed to wear different hats through the day, teaching, research, advising students, like communicators like this. One has to be willing to do these kind of things. Have a vision, right? Like take some of the problems we are interested in, effectively communicate it to funding agencies, communicate it to interested people like you, get you people like you excited, and so on. Right. So life, as if you like such kind of jobs, then definitely. And then one more big thing is that you are your own master. No, there's nobody is telling you in IISc for sure. There's nobody who's sitting on top of me saying, "You, I should work on this. I should work on that." I pick up topics of interest to me and work on that, and convince the funding agencies, convince people that this is the cutting edge research one has to work on. And then you will be evaluated for that. No, there is promotion, there's tenure track. People will evaluate you on what you have done, and then one has to fare well. No, whatever you have told us. What you are doing is important should really be important in the eyes of your peers, basically. Then only you will get promoted, right? So life as a professor is interesting in that respect. In a company, no, there will be a lot of other factors. Your manager will tell you what you need to work on. Your how the company is doing in terms of money flow will decide whether you have the job or not, right? So such kind of things will occur in an industry job. While professor job is a little bit more secure, though the pay may not be that high, but then you have a lot more freedom to choose the kind of problems you work on, basically, and that's where the excitement comes in. How to become a professor? Obviously, you have to do a PhD. That's a basic requirement for being a professor in IISc and IIT and so on. And then you should do cutting edge work. No, we are looking for real superstars in their respective areas. And quantum is an area definitely IITs and IIScs is looking for. You have to publish in good venues and set up or establish your portfolio that you are an expert in that field, right? And then do postdoc also, sometimes or sometimes not. Do postdocs to specialize further in that area. Prove that you're not always in the shell of an advisor. You can become independent as a postdoc. Then come back. And there are definitely calls, no, in papers and in the respective IITs, IISc websites. There'll be calls for job, no, for professors at different levels. You can see and then apply for that, right? And then a committee will review that and decide whether we want to have that person or not, and then take it forward. Right? That's how one would become a professor. Right? I hope I have answered
Uh,
the question.
if anybody has any more questions, you can just pop them in the chat box.
Okay, I don't see any other questions.
Okay. Thank you, sir. Thank you for this enlightening lecture, and your insights and your knowledge and experience have really broadened the understanding that we have of this field. And we are grateful for your time and effort that you've dedicated to share your expertise with us. So, on behalf of the Electrical Communication Engineering Association, I would like to express our sincere gratitude to Dr. Raghunathan for taking time out of his busy schedule to speak with us today and to mentor the next generation of innovators. This is Sana Shingade from ECEA Association signing off.
Thank you very much. I really enjoyed this. Thank you.
Thank you, sir.